Let's discuss the next generation of AI. Today's AI is not getting closer to AI's goals, and that's a problem. Sure, there's a lot of activity in AI around LLMs like ChatGPT, with outrageous hype claiming human-level AI is approaching, but that's easy to falsify. Breathless announcements for improving on artificial benchmarks are no match for science, even if there are billions of dollars of investment involved chasing trillions of dollars in value. In science, we can see goals that are stuck despite benchmark successes. It's hard to quickly critique the lack of progress in AI, so let me talk through some issues today and then talk in more detail in the coming weeks. But always keep in mind that AI should aim at human-level skills and not allow current limitations like errors or lack of trust to be accepted or, worse, to become the goal. After all, goals can be whatever we want them to be. So what is the goal of AI? Well, let's see what others think. First, this is from Microsoft Copilot. I've asked it the question, what is strong AI? And it's come back and said, strong AI, also known as AGI or artificial general intelligence, is this intelligence that possesses human-like cognitive abilities. So for me, human-like cognitive abilities are being able to see, to move, to pick up things, to read. That sounds like the right goal. And here, general intelligence, it's got to be capable of understanding, learning, and applying knowledge across a wide range of tasks and domains, just like a human. So you would imagine that given AGI, a robot would be able to walk in, the embodiment of this artificial intelligence. It could pick up books and it could read through the books, learn things from it, just as a human would do. So AGI looks like human emulation. Let's validate what IBM thinks. So here's an IBM article on strong AI, which is now being referred to as AGI. It would possess intelligence and self-awareness equal to those of humans. So again, it's a very complicated thing to get to because we're talking about solving basically everything. So we're solving our sensory control, our motor control, the integration, our decision making, our ability to move around the world and learn things like children can do. So it's quite a challenge. Let's have a look at then what's being published now as the path to AGI. And you can see here, it's talking about the quest for AGI, and OpenAI has introduced this 5-level framework. And in this case, it starts with chatbots, and then it moves on to reasoning agents, innovators, organizations. And this pinnacle is performing the collective functions of an entire organization. Well, that's not really on the AI, that you could have a whole bunch of robots doing that. So organizations is simply a bunch of robots doing something, you would think. And as we go back earlier here, these are agents with autonomy, and reasoners are human-level problem-solving abilities akin to someone with a PhD. So remember, the person with a PhD has studied a very narrow area, and they become a world expert in it, and they've written a thesis on it. So they're very good at that area. So in this case, they have to have the problem-solving ability of somebody that's already got a PhD. It just doesn't seem like this has got anything to do with the goals of AI. It's very good if all you've got is a text generator, because you can imagine a text generator doing these types of things. So let's keep moving on. That was just an announcement about OpenAI's plans. I've gone here into ChatGPT and I've asked it the question, what are the levels of AGI? And it starts with narrow intelligence. This used to be called weak AI. Then it talks about artificial general intelligence. This used to be called strong AI. And here, it's defining AGI as the capability to understand, learn, and apply knowledge across a wide range of tasks, like a human. Well, if it's just like a human, it has to be able to read, walk, use its vision, be able to speak, ask questions. So it looks like it should be the same as the old definition of AGI, but the capabilities exclude the motor control. It excludes the sensory control and the motor control. So it seems to be excluding robotics as part of this, which is then going to ask the question: how could a machine that only handles text be AGI? Because if it can't see, it's severely limited in its capabilities. And then there's some other levels here. So while we're looking at AGI, for me, self-driving cars comes into this. So here's the Wikipedia page on self-driving cars. Let me just make that. So here's the Wikipedia page for autonomous cars. And you can see here that it could be self-driving cars, autonomous, driverless car, robotaxi, a whole bunch of different names for it. But the reason I think this is very interesting is that self-driving cars, you would think, are at the pinnacle of AGI, because it's got to be able to do things like recognize dangers. It should be able to read signs. It should be able to communicate with people stopping traffic to make decisions of what to do. A fully driverless car sounds like a really good application for robotics. So when we scroll down here, this has, just like OpenAI, a definition of different levels of automation. SAE automation level. So SAE, I think, is the standards body. And it's come up with level 0 is no automation. Level 1 and 2 are Luth driver's assistance. So the driving is still being controlled by the driver. We then get into the driver's simply sitting there and has to act if the machine tells it to. And in this case, if the driver doesn't respond accordingly, the car is still able to control the safety. And finally, level 5 is you don't even need a steering wheel. The car is just going to drive and presumably communicate with language like any other person. So it was important for me to just demonstrate the differences there with the levels of now AI and the levels of driverless cars. And I would just point out that the goal of AI should be to solve the problem, not to create a whole bunch of benchmarks or compromises where the only one that really matters is the 5th level, and then these other ones don't necessarily have any direct path to the solution. So what have we just seen? Strong AI should fix the long tail of driverless car problems using its vision and world knowledge. And OpenAI has an AGI plan that excludes the hard problems of AI that will leave it blind, deaf, mute, and paralyzed. For marketing purposes, for their marketing purposes at least, that's fine, but their AGI is moving the goalposts to avoid solving the problems of AI. And worse, industry, government, and educational institutions may blindly follow them due to the scale of their investments. These are very large companies that are involved in this AI. There's a lot of money coming in, and they're spending a lot of money. If you're a university, would you say, look, OpenAI, I don't think you're on the right path there, or would you just take the money and work with them on their plan? And I think that's one of the challenges that we have in the scientific community to deal with the pressure of large investments. My point is that there's a big deviation between the goals of AI and OpenAI's definitions that suit their LLMs limitations, but not the more sensible AI goals from the past. Along these lines, the ultimate goal for autonomous cars requires animal-level sensory and motor control, probably at human level, to handle emergency situations. What I mean by that is, should it drive off the road into a stationary truck to avoid hitting a child sitting in the road? It may well kill us in the car. Or should it continue on for personal safety if it were a small animal on the road, and we would protect ourselves by not driving into the truck, but potentially harming that animal in the road? And those are quick decisions, of which there are many, many, many needed for human-like safety when we're driving a car. Now let's move on to human language, because that's been my focus in AI for many years now, certainly the last 20, because the types of things that you can really use to prove out a brain theory center around language, because language doesn't require robotic muscles and bodies and vision systems that are mimicking what animals' systems are like. So the goal, if machines could speak our language, imagine how much more useful they'd be. And this has been known as natural language understanding, or NLU. And a number of different approaches have been taken, including most recently the ones at my company, Pat Labs. The Noam Chomsky formal model from the 1950s failed for NLU since it's too ambiguous with its reliance on syntactic units called parts of speech. A lot of effort was tried from the 50s to the 1990s, and without success. Human languages haven't been emulated. And then computational linguistics, also based on the syntactic model, failed from the 1990s to around 2015, 2016. It's just too ambiguous, again, even for machine learning to handle. LLMs now have significant problems with their statistical design as well. And the most obvious are its errors in making stuff up. But for use in other applications like agents, LLMs don't provide what is asked, but instead they generate text as an answer. That's what an LLM does. You put something in and it generates text as an answer. But without understanding what was asked and finding what the answer is, strategies to deal with the limitations are additional subsystems. And ultimately, lack of backwards compatibility with statistical data models are expensive to maintain. Now, as explained by Tom Dietrich, the professor from Oregon and a pioneer in machine learning, LLMs have a statistical model of a knowledge base and should split knowledge from language. That's his recommendation, which leads to the cognitive science model. My brain model, Patom theory, or just PT, stores patterns in their edge positions where they're recognized through the senses and then links them together. The model allows any connected brain region to serve patterns to subsequent regions, as we see from brain damage, but without encoding them. It removes the need for search in the system since patterns are atomic. You can just follow their links. A pattern atom is the one pattern that represents itself in the system. In conjunction with role and reference grammar linguistics, or RRG for short, the split between languages' words and phrases on the syntax side and their mapping to meaning in context creates the split between a language and knowledge, as Tom Dietrich suggests. Now let me show you a model of this so that I can just discuss it in a little bit more detail. Okay, so what we can see at the top here, this is the method that's, I think, pretty well accepted. This is how language works. We get sensory input. So in the case of speech, we're hearing sound. It's coming through the auditory cortex, and we can recognize that those sounds represent words. The words then are combined in phrases in order to then link to meaning. Now, in the work that I've done in creating conversations with machines using only meaning, what we're doing is we're finding these sequences of letters that represent words. We then take the meaning of those words and we combine them into phrases, and then we make sure that it has some sort of meaning. And we do this repetitively until we've understood the entire sentence. But once you've done that, when you've got this new sentence in, the question is this new context? Do I need to add this to my existing context, or is it a duplicate of something I've already seen? Because if I say the same thing again, I should go back and say, I know. Is it a question? In which case, if somebody's asked me a question and I choose to answer it, I can go and have a look at what's in context and come up with an answer. Or possibly if I just said something randomly like Alan Turing, I don't want to just go and do a search and give the person a search result. I want to go and say, oh, do you mean my neighbor Alan Turing, the young kid, or do you mean the code breaker from World War II? So those types of clarifications are needed because what the human brain is required to do is to learn through experience. So we need to understand what the elements are that we're manipulating, and this is part of the pragmatics part of linguistics or science, because I think it's also a philosophical concept. So the idea of pragmatics and discourse pragmatics in this case, there's a lot of theory that explains how we talk to each other in order to convey useful knowledge, which we can then store and rely on because we've stored all of that in context. The other example, let me see here. This other example here is what we see from a large language model. So we get text in, the text is converted into tokens, the tokens get converted into their vector representation. And then once we have the string that represents the prompt, we start this auto-regression loop. We get the system to predict the next word. The next word is added to the list of words that we've had so far, and then it just keeps repeating to produce sequences of predicted next words. And we then use those next words as our answer. So you can see the challenge here. We can pass the words that it generates to some other processing system, but now we're just back in the 1960s world where you're generating something and you're looking to write a program for it. But our brains don't seem to have anybody writing programs for them. So why would we build systems that basically move the problem from we don't understand this language to now we don't understand the response that was generated by the large language model? So the problem that we have, if you compare this to the model up here, when we talk about context, there's actually two pieces of context that are quite distinctive. There's immediate common ground. So this is the current conversation, the things that are currently going on that we can refer to. When you're having a conversation with someone, you know what you've said to them, you know what they've said to you, and you're able to then save a lot of time by referring with pronouns and proforms to the things that they've been talking about. If you didn't have that, if you only had general common ground, that's our background knowledge, it would be much slower to speak, because if I said, he's a good guy, you could immediately come back and say, oh, you mean Alan Turing, or you mean your brother, or you mean the guy across the road. What do you mean by that? Because you're not limiting your conversation to the current immediate common ground. So if you're now an LLM and you want to deal with what's currently happening, you've got a problem, because what the system does is it gets the next word out of its large language model, and the large language model was trained on millions of documents. How is it supposed to keep track now of what it's currently talking about and then make any comparisons in order to bias the next word generation in some way? Again, you can we'll have some other type of processing to make it work, but we're talking very complicated subsystems now. And are we making just the whole concept of AI exponentially harder because we have a tool that works for certain things, the LLM, but then how are we going to integrate this tool? Wouldn't it be better just to start with something that's better and then get that system to do more than an LLM can do? As you could see in that example, moving parts for human language need words and phrases linking to meaning and context. That comes from role and reference grammar. And context isn't trivial, nor is it language specific. Context can come just from the meaning of what's being said, and that allows any human to integrate senses with meaning because it's not language specific. It's an important point that one of the benefits we get through evolution is a very rich knowledge representation that other animals like dogs and cats share with us, where they understand many things that happen in the world, and we have on top of that language that we can bring to bear on it. But by other humans not having language-specific meaning in the same way, all humans can share similar representations that come from our sensory integration in our brain. Anyway, systems based on this cognitive science approach promise to cost something like a tenth or less of an LLM, while adding important technical benefits like testing and backwards compatibility and low power consumption. So let's go to the real goals of AI. AI holds the key to killer applications of a scale we have never seen before. It's easy to see the trillions of dollars possible through successful robotics and other technologies. The goal of agents, for example, can help users in their own language, and it's very compelling. It's one of the reasons the 2014 bubble for chatbots was so strong, at least as long as the underlying technology was machine learning, from what I could see at the time. But working AI will enable lots of stalled projects to progress because it can provide the missing pieces currently factored out of today's compromised systems. I discussed the killer apps in my recent book, but imagine human-level capability for speech recognition, automatic translation, transcription of languages accurately, driverless cars, home robotics, lossless knowledge storage, which would enable the production into any language, and language learning robots and general online agents. the potential for AGI and language understanding in particular is extremely large. And for me, cognitive science is the next generation of AI because it will enable these stalled projects to be completed. These are good enough projects in today's tech giants, but they're not really good enough. It's just that there's no way forward without understanding language, which is typically the missing piece of problems today. Speech recognition, for example, it's good, but it doesn't work like a person, and so it's just an error-prone tool. So too, automatic translation is an error-prone tool. It's good, but not good enough to rely on it. Similarly, automatic captioning is error-prone. As a reader, you can work out what was probably said, but you often get rhyming text. Similarly, LLMs are error-prone. So too are conversational agents. They're error-prone. So rather than generating probable text, understand and clarify what's received as per the cognitive science model. And clarification is at the core of communications. It's not just answering, as I showed in that diagram. By understanding that language is communicating, that promises to transform today's AI tools into ubiquitous tools. It's been the holy grail of Silicon Valley for decades, leading to today's voracious appetite to invest in AGI companies. But they should be AGI. What's the business of AI? The world of investment is keen to see human-level intelligence in machines, and the current investment model seems to value LLMs on that path. But LLMs are easily disrupted, as we've recently seen with the Chinese company DeepSeek, that created an LLM for roughly 5% of the cost of its American competitors. Cloud hosting providers have been the big winners in the recent AI race because they're the ones involved in collecting money for the training of these systems. But even so, the US government is now supporting an initiative to build new data centers to deal with the excessive power and data needs of large language models. Imagine if we could simply usher in a better model that doesn't require that. And just as announcements from DeepSeek can devalue the speculations on the LLM form of AI, the real competitor remains cognitive science implementations, such as the ones we developed at Pat Labs. Rather than needing billions of dollars of new data centers and power sources, new systems of cognitive science-based AI could run on laptops and cloud servers like other modern applications. Just as the human brain uses about 12 watts of power, so too can we use cognitive science to drop the cost of AI towards those levels and with more accuracy. The next generation of AI is going to win. Let me tell you why. The evidence against LLMs being a long-term proposition have been clear for some time. Simply in terms of cost, without a monopoly and with lack of trust on their output, if a trustworthy alternative arrives, who perseveres? And just following Professor Dietrich's suggestion, say you're an Amazon. To interact with users who want to buy their products, why should they pay for the knowledge in the LLM of molecular biology, space travel, theoretical dance, and other topics in order to use language to find or explain what their products are? And without context, how can conversations be controlled? It's a missing link in the architecture of large language models. Thanks again. I'm going to explore these questions more in upcoming videos.